So the first problem is from Electric Circuits and Networks, which was asked in GATE 2015 for 1 mark. A series RL circuit is excited at t equal to 0 by closing a switch as shown in the figure. Assuming 0 initial conditions, the value of d square I by dt square at t equal to 0 plus is. So we are given an RL circuit connected to a DC source and a switch. At t less than 0, the switch is open. That means there is no DC source connected to the circuit. And it is given that the initial conditions are 0. That means at t less than 0, there is no current flowing through the circuit. Or else the current flowing through the inductor at t less than 0 or 0 minus is 0. So this is inferred from this sentence. Now we are asked to find the value of d square I by dt square at t equal to 0 plus. So when t is greater than 0, the switch is closed. So the DC voltage is applied across a series connection of resistance and inductance. So this is V. Let the current flowing through the circuit be I. This is R and this is L. I hope you read the question and understood what is asked. Is the question clear? Okay. So now we will apply Kirchhoff's voltage law. So when current flowing through this from one end to other end, the point where the current enters is positive potential and negative potential, because current always flows from higher potential to lower potential. So this V is nothing but IR plus L di by dt. Now from this, I'll find di by dt, which is nothing but V minus IR the whole divided by L. So the value of di by dt at t equal to 0 plus we have to find. Then only we can find d square I by dt square at t equal to 0 plus. So di by dt at t equal to 0 plus is V minus I at 0 plus into R divided by L. Now we know that the inductor does not allow sudden change of current. By that principle, whatever was the current through the inductor at 0 minus, the same current will be through the inductor at 0 plus. So since the whole network current I is same as inductor current, I of 0 minus is same as IL of 0 minus and I of 0 plus is same as IL of 0 plus, which is nothing but 0. So this value is 0. So what is di by dt at t equal to 0 plus? It is V by L. Now let us differentiate this equation once again. So d square I by dt square is V. Now what is dV by, I'll split di by dt as V by L minus IR by L. Now this is derivative of V by L minus derivative of d by dt of IR by L. Now L is constant, R is constant. So this is 1 by L dV by dt minus R by L di by dt. Now V is given as a DC source. So dV by dt is 0. So this comes down to minus R by L di by dt. Now we are asked to find d square I by dt square at t equal to 0 plus, which is nothing but minus R by L di by dt at t equal to 0 plus. Now which we already found before, which is V by L. So this is minus R V by L square. Option D is the answer. So we can actually, by initial guess, we can eliminate option A and option B by dimensional analysis. Now you know that the voltage is given by L di by dt across an inductor. So this dimension of V is volt, dimension of inductance is Henry, dimension of di by dt is ampere per second. So what is the dimension Henry? Which is voltage second by ampere. So when you inspect the dimensions of the option, we are asked to find d square I by dt square. The dimension of d square I by dt square is ampere per second square. Have any doubt in that? The dimension of d square I by dt square is ampere per second square. So the dimension of V by L is what? Dimension of V, which is V, option A, by inductance dimension is Henry. So we know that Henry is volt second by ampere. So this will come out to be volt second by ampere. So this is ampere per second. So the first option has a unit of di by dt. So we know that the first option is not the answer. Now second question, you know that V by R is voltage by resistance, which is nothing but only ampere. The dimension is only ampere, so that is also not the equation. So it can be either C or D. So we have to continuously do the analysis. If option C was something else, then you can do the dimensional analysis. So at first, try doing dimensional analysis, and by through dimensional analysis itself, if you can solve the answer, then it is easy. Else, since we have two options in doubt, we are going for the analysis. So is the problem clear? Okay. So the second problem is also from networks. So we have a three-phase balanced system. In the given network, V1 is 100 angle 0, V2 is 100 angle minus 120, V3 is 100 angle plus 120. The phasor current is. So we are given a three-phase system where V1 is 100 angle 0, V2 is 100 angle minus 120 and V3 is 100 angle plus 120. I hope you are familiar with phasor concepts. So the angle between them is 120 degree. Let us suppose a common ground. So this is, and the current through minus ji1b I1 and ji1b I2. Now you apply KCL at this node. I1 plus I2 plus I is equal to 0, or I is equal to minus I1 minus I2. Now what is I1 and I2? I1 and I2 can be obtained by dividing the voltage across these elements by the current through them. Dividing voltage across the elements divided by the impedance. Now we see I2. Let this be point A and point B. So I2 is the voltage across AB divided by J1. Now what is the voltage across AB? If this point is grounded, the potential A is same as V2 and the potential B is same as V3. Is that clear? Okay. So VAB means V2 minus V3. So vector I2 is vector V2 minus vector V3 by J1. Similarly, current I1 will be, this is, let it be C, let it be D. C is same as V1 and D is same as V3. So this is V1 minus V3 by minus J1 impedance. So our current I is minus I1 minus I2. This is nothing but minus I1 means minus of V2 minus V3, which is V3 minus V1 by J1, minus of V1 minus V3 by minus J1. So this is V1 minus V3 divided by J1. So now V3 and minus V3. V3 by J1 and minus V3 by J1 cancels out. Sorry, this is I2 is V2 minus V3. Did I made a mistake? Okay. Minus I1 is V1 minus V3 by J1, because this minus I cancelled with this minus. Now I2 is V3 minus V2 by J1. So cancelling V3, oh, I made a mistake. I is minus I1 minus I2, which is minus of I1 is V1 minus V3 by minus J1 I2 is V2 minus V3 by J1. So this is V1 minus V3 by J1 minus V2 by J1 plus V3 by J1. Minus of minus is plus. So here V3 gets cancelled out. So I becomes V1 minus V2 by J1. Now to solve V1 minus V2, let us use help of phasor diagram. So V1 is this and V2 is lagging V1 by 120 degree. V1 minus V2 is same as V1 plus minus V2. So minus V2 will be here. It will be 180 degree apart from V2. So this is minus V2. V1 plus minus V2 is we are adding both phasors. I hope you are familiar with phasor addition and subtraction. So this is nothing but the line voltage. So if angle between V1 and V2 is 120 degree, then the angle between V1 and minus V2 will be 60 degree. And since magnitude of V1 and magnitude of V2 are same, their resultant will be 30 degree from both the vectors. The general expression for vector addition is V1, a vector VA plus vector VB is nothing but root of magnitude of VA square plus magnitude of VB square plus 2 times magnitude of VA to VB cosine of angle between them. So in this case, V1 plus minus V2 is magnitude of V1, which is V square, plus magnitude of VB, which is also V, plus 2 mod V, cosine of angle between them is 60 degree. So by solving this, you will get it as root 3V angle 30 degree. So this resultant is root 3 times the magnitude with an angle 30 degree from both. Hence our current I becomes root 3V angle 30 divided by J. Only V1 minus V2 we solved. So root 3V is magnitude of V1, V2, V3, which is nothing but 100. So this is 100, angle 30 minus J is 90 degree. So when you take from denominator to numerator, you have to subtract the angle. So this is root 3 is nothing but 1.732 times 100 angle minus 60, which is 173.2 angle minus 60 degree ampere. So you get the answer as option A. Is it clear? Or should I explain once again? Okay. So moving on to next question. This is from DC machines. Asked in GATE 2020 for 2 marks. A 250 volt DC shunt motor has an armature resistance of 0.2 ohm and a field resistance of 100 ohm. When the motor is operated on no load at rated voltage, it draws an armature current of 5 ampere and runs at 1200 rpm. When a load is coupled to the motor, it draws total line current of 50 ampere at rated voltage with a 5% reduction in the air gap flux due to armature reaction. Voltage drop across the brushes can be taken as 1 volt per brush under all operating conditions. The speed of the motor in RPM under this loaded condition is closest to. So we have a DC shunt motor. DC shunt motor means the field will be connected in parallel to the armature. So here the applied voltage is 250 volt. DC shunt motor has an armature resistance of 0.2 ohm. So the armature resistance is 0.2 ohm and field resistance is 100 ohm. When the motor is operated on no load, so let the no load condition be represented by subscript 1. So at no load condition, when rated voltage is applied, it draws an armature current of is IA. So no load condition is IA1 is 5 ampere and it runs at 1200 rpm. When a load is coupled to the motor, so when the motor is connected to a load, It draws total line current. Line current is this IL. So let that case be case 2. So the line current in case 2 is 50 ampere at rated voltage with a 5% reduction in the air gap flux. So if the air gap flux in the first case is K phi 1, in the second case it is K phi 2, it is 5% reduced. So it is 0.95 times K phi 1. Voltage drop across the brushes. So there, when we represent the motor, these two parts are brushes. So there is a brush drop of 1 volt per brush. There are total 2 brushes in the machine. So if you include the brush drop in the equivalent circuit, brush drop will be here, then the armature, then another brush drop. So this is 1 volt, this is 1 volt, this is the back EMF. Now the speed of the motor in the second case, N2 is what we have to find. For a DC machine, the relation of speed with back EMF is given by K phi, flux, field flux times the speed in radian per second, or the back EMF is proportional to the field flux times the speed in RPM. So we have to find N2. So EB1 by EB2 is K phi 1 by K phi 2 times N1 by N2. So from here, N2 is K phi 1 by K phi 2 times EB2 by EB1 times N1. Now K phi 1 by K phi 2 we already know. K phi 2 is 0.95 times K phi 1. But we don't know what is EB2 and EB1. N1 also we know. It is 1200 RPM. So we have to find the back EMFs in both the cases. In the equivalent circuit, we know that there is brush drop involved. So in case 1, when we apply 250 volt, there is a brush drop of 2 volt. This is EB1. Already given the question that this current is 5 ampere. This resistance is 0.2 ohm. This is 100 ohm. So this 250 volt will come here same as 250 volt. So 250 volt if you apply KVL, it is 5 ampere into 0.2 plus 2 volt drop plus EB1. Here you will get EB1 as 247 volt. Now in the second case, brush drop will remain at 2 volt because in the problem it is given that the brush drop is 1 volt per brush under all operating conditions. So here this is EB2, same 100 ohm, this is 0.2 ohm. 250 volt is applied. Now here it is given that line current is 50 ampere. So if this is 50 ampere, the armature current IA is this and field current IF is this. Second case it is 2. So IA2 is 50 ampere minus IF. IF is nothing but 250 by 100, which is nothing but 2.5 ampere. So your IA2 will come out to be 47.5 ampere. So your EB2 will be 250 volt minus IA2 times RA minus 2. So it will be 238.5 volt. So you got EB1 and you got EB2. So you can find your N2. So N2 is 1 by 0.95, EB2 you get it as 238.5, EB1 is 247, N1 is 1200, so it will come out to be 1219.6 RPM. So it is closer to option C is the answer. Is it clear? Okay. So that's all for today's class. Meet you on next Thursday. Thank you.